show you how we can use Descartes' rule of signs to figure out the possibilities for what the zeros could be, and then use that to strategize in doing what we've been doing, which is finding all of the zeros and factoring things. Okay, so if I take a look at this polynomial has a non-zero constant. So I know that 0 is not a 0 of this polynomial, because if I plug in 0, I just get that constant term. Okay, so that means all of my zeros are either positive real, negative real, or not real at all. I'm going to try to fill out this table listing all of the different possibilities. And there are a couple of things I want to note here. For the non-real ones, whatever I put in this column must be an even number. That's because I've got real coefficients here, and so if I have non-real zeros, they come in conjugate pairs. So I'm never going to have an odd number here. Okay. The other thing I can do, and I'm going to just go ahead and write this in, is that the total number of zeros, now I'm counting multiplicity here. So if I have 2 positive zeros, it could be that they're the same one, just with a multiplicity of 2. But the total, counting multiplicity, is always going to have to be 3. Okay, that's because this is a third-degree polynomial. Okay, so let's use Descartes' rule of signs. Basically what I'll do is I'll list the possibilities for the positives and the negatives, and then if they don't already add up to 3, I'll fill in the remainder with non-real ones. If I don't get an even number here, that's going to tell me that I made a mistake somewhere. Okay, so if I take a look for the positive reals, if I take a look, everything is positive. There are no sign changes. So there are going to be no positive real zeros, period. Can't have any. That's actually really nice to know. Okay. Let's take a look at f of negative x. So that's going to be negative x cubed plus 3 times negative x squared plus 12 times negative x plus 10. Essentially what happens when I plug in a negative x is all of the odd powers are going to change sign. All of the even powers, including the constant term, are going to stay the same. So I'll get the opposite of x cubed plus 3x squared minus 12x plus 10. Now it is very important that I've written everything in descending order here, because I'm taking advantage of the fact that the size of the terms goes with the power of x. Okay, so here I've got this is negative, then we've got a positive, then we've got a negative, then we've got a positive. So sign changes, 1, 2, 3 sign changes. So for negative real zeros, I could have 3, or I could have less than that by a multiple of 2, because if I lose 1, I lose a pair. So 2 less than that would be 1, and those are going to be my only options, because I can't go 2 less than that and still have a non-negative integer. So with either of these possibilities, I know I have 0 positive real roots. I know the total has to be 3 for every possibility. Well, 0 plus 3 is 3, so if I have 3 negative real roots, I will have no non-real zeros. Sorry, I'm using the word root. I should be using 0 because that's the vocabulary of our textbook. I think I've mentioned some textbooks call the zeros of a polynomial the roots of a polynomial. All right, so 0 plus 1 is only 1. I'd have to here have 2 non-real zeros in order to bring the total up to 3. And notice that is an even number. So this is really helpful, because now I know if I'm going to use the rational zero theorem, I want to check the negative ones. I'm guaranteed that there's got to be a negative real root. Now I'm not guaranteed that it has to be rational, but I'm pretty suspicious. Actually, I'm not guaranteed by this that it has to be rational, but because all of my coefficients are rational, and I know that irrational ones come in pairs, I can tell that I'm going to actually have to have one rational one at least. But even if I didn't see that, the fact that I've got to have real negative roots means let's try the real negatives, because I can, the negative rationals, because I can come up with a list of possible rationals. So now I'm going to use my rational zero theorem, So let's mind our p's and q's. P has to be a multiple of 10, so plus or minus 1, plus or minus 10, plus or minus 2, plus or minus 5. 3 doesn't work, 4 doesn't work, 5's already on the list. Q is just going to be plus or minus 1, because it's got to be a factor of my lead coefficient. So the possible rational zeros are just plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. Before this video, we would have said that's 8 possibilities. Now I'm going to say that's 4, because I know none of the positive ones work. So I'm just going to try the negative ones. All right, so let's use our synthetic division. We've got 1x cubed, 3x squared, 12x, and 10. Quick check. Constant x, x squared, x cubed. I'm feeling good. Let's try negative 1 first. So I bring down the 1. We multiply to get negative 1. We add to get 2. We multiply to get negative 2. We add to get 10. We multiply to get negative 10. We add to get 0. Oh, lovely. This is very exciting. Okay, so we've right off the bat found one negative 0 and a corresponding factor. I always forget to give you the directions for things. Let's find all the real zeros, all the complex zeros, and let's factor over the reals and factor over the complex numbers. Okay, so at this point, I can say that f of x is going to be x plus 1. That's x minus this 0. And then this encodes the other factor, which would be x squared plus 2x plus 10. Okay. So, and let me just over here keep track of things. If I want to find the real zeros, the complex zeros, I want to factor over the reals, and I want to factor over the complexes. We have already found negative 1. That's both real and complex, so that'll go on the list for both of these. The corresponding factor of x plus 1 is going to show up whether I'm factoring over the reals or over the complexes. And now I just want to see if I can break this up anymore. Now this one is quadratic. So I no longer need to use trial and error. I could see if I could factor that. It's not going to factor using my factoring techniques. Now, I know it factors over the complex numbers because we've got the linear factorization theorem. But using my techniques of trying to unfoil, it's not going to unfoil. So let's use the quadratic formula. Here my A is 1, my B is 2, and my C is 10. So x is going to be the opposite of b, plus or minus root b squared minus 4ac, all over 2a. That's going to give me the opposite of 2, plus or minus the square root of 4, minus 4. I can write. Square root of 4 minus 4 times 1 times 10. All over 2. Let's see, that's going to be negative 2 plus or minus the square root of, that's 4 minus 40, that's negative 36, all over 2. Since there's a negative under the radical, this is going to be complex and not real. Now that simplifies to negative 2 plus or minus 6i all over 2. And standard form for complex numbers, I'm going to get by distributing that 2. So negative 2 over 2 plus or minus 6i over 2. I want to have the real part plus the imaginary part times I. Notice that's negative 1 plus or minus 3i. Okay, so it turns out this is what we had. We had one real negative and two non-real zeros. So just listing our zeros, there was only the one real zero. Complex zeros are negative 1 plus 3i, and negative 1 minus 3i. Factoring over the reals, we were actually done at this step, because over the reals, that's an irreducible quadratic. But factoring over the complex numbers, for each of these new complex zeros, I've got a corresponding factor. So we're going to have, actually let me write this out over here. We'll have x minus -1 plus 3i, and we'll have x minus -1 minus 3i. And I'll want to just distribute that negative. So this becomes x plus 1 minus 3i, and this becomes x plus 1 plus 3i. So I'll add in those factors over here, x plus 1 minus 3i, x plus 1 plus 3i. And then I want to do a quick check when I'm finding my factors by just taking x minus a 0. I've got to check, do I have the right lead term? Here the lead coefficient was 1, so I don't need to adjust with a constant factor. But if this had been a 2x squared here, I'd have to throw in a constant factor of 2 as well. All right, excellent. So it was very helpful to know to start with the negatives, because as a general rule, I find positives easier to work with than negatives, so I would usually start with the positives. Here I knew not to because I used Descartes' rule of signs. Now, some of the homework will explicitly ask you to create a list of possibilities. Some of it will go further and say, after you create this list, actually go ahead and find all of the zeros. Some of the homework will just say, find all of the zeros, and you can choose whether you want to use Descartes' rule of signs or not. If you've got a really long list of possible rational zeros, it might be helpful to strategize so that you can figure out where it makes more sense to start, with the positive ones or with the negative ones. If you've got a fairly short list, you might decide that it takes more time to generate this table than just to go through the list and try all of the possible rational zeros. So just make sure you're reading the directions. I could test you directly on Descartes' rule of signs by asking you to create a table like this. Or I could just give you a problem where I say, find me the zeros, or factor, or possibly do all of these things, okay? In which case you could choose whether you want to use this strategy or not.